Today we're going to be talking about Big Bang Cosmology. What is Big Bang Cosmology all about? What does this mean for those of us who are Christians or those of us who believe in a God who's a creator? Last week we talked about the geological history of Earth and how scientists who were devout Christians introduced and developed the scientific idea of vast periods of geological time. We also spoke about how modern young Earth creationists reject this idea of vast geological time, and an idea that again was originally introduced to the world by devout Christians who were also geologists. There might be good reasons to hold young Earth creationism if this view was taught unequivocally by Scripture. However, as we discussed last week, it is not. We found out that unless you hold the visions of Seventh-day Adventist prophetess Ellen White to be divinely inspired and believe that Ellen White, in fact, has more authority in interpreting the days of Genesis 1 than the writer of Genesis 2, and if you want to know what I mean by that, then you can watch the video for last week's class. But unless you hold Ellen White to be an inspired prophetess whose authority is pretty much equal to the Bible, then there are no good reasons to hold young Earth creationism. Again, this is all recap from last week. But today we are going to speak about another area of modern science that was introduced by scientists who were devout Christians. And this time they were physicists and cosmologists who were devout Christians. But again, this area of science is rejected by all the leading young Earth creationists. This area of science is the standard model of cosmology, often referred to as the Big Bang Theory. What do I mean by this term cosmology? What is cosmology? Well, cosmology is the study, thus the ending logi, or logi, like logic, the study of the whole universe as an organized, structured entity. And this entity is the cosmos. This is not to be confused with another term that you hear sometimes when people talk about stories of the beginning of the universe, and this is a term cosmogony. And this is an account of how the structured universe came into being. And you can hear, if you think of like the Jenny ending versus the ology ending, you have Jenny like Genesis, genetics, generations, genealogy. That has to do with birth. And so that's an easy way to tease out these two terms. I'm not going to use cosmogony in this lecture, but what's important about stories of origins is that they're often rooted in understandings of the cosmos. The way that the universe is thought to be dependent on the way it came into being. In other words, the character of the cosmos is often understood to be a reflection of its origins. The other reason that cosmogony is important when we think about cosmology is worldview. We all have a worldview, and a worldview is an understanding of the world that guides the way that we live in the world. Our worldview shapes our answers to the big questions, such as who am I? Why am I here? Is there meaning to life? And so on. Your worldview is shaped, at least to some degree, by the cosmology you or the community that you're part of holds. The link between cosmology and worldview, in fact, leads many people to expect modern scientific cosmologies to provide answers to the big questions in life. So if you're wondering, well, why are we all here? Your answer might come from your view of the universe. Well, where did the universe begin, right? And so I think it's natural for a lot of us to couch those individual questions in larger questions, like, well, why does anything exist at all? Cosmologies go back to the very dawn of human writing. We find that your very first people who were writing this stuff down were thinking about these stories of where do we come from. What's interesting in the vast majority of ancient Near Eastern cosmologies, and the Near East is where the Hebrews originate from and where we get our Bible from. But the vast majority of these ideas of the early ideas of where the world came from, that they saw the material world as a whole as pre-existent, and that there was not an absolute beginning to the material world. So in your Sumerian cosmologies of your 3rd millennium before Christ, we see that the sky and the earth are seen as eternal, and they're seen as gods. The creation of life takes place through the procreative union of the god An, who is heaven, and the goddess Antum, who is earth. This union fertilizes the earth to produce life. In the Akkadian Enuma Elish, and this is also Babylonian creation epic, we find similar themes. The primeval waters, who are a god Apsu, and a goddess Tiamat join and give birth to the lesser gods. And in this story, Tiamat then is slain by her son Marduk, and her body is cut in two, and her corpse, one half of her corpse makes the earth, and the other half of her corpse makes the sky. And so, for ancient Babylonians and Akkadians, you're literally living on a corpse in a sense. If you take these stories literally, we don't know exactly how they took these stories or not, whether poetically or literally. But this is the basic idea. Often creation is either from procreation, or creation is from some sort of cosmic battle, primeval battle. But these are battles of forces that are part of nature and exist to all eternity, as far as we can tell. The idea of a body making up heaven was also part of the Egyptian myth. Here we have the Egyptian goddess Nut. According to the Egyptians, during the day, the heavenly bodies, such as the sun and moon, would make their way across the bottom of her body, and then at dusk, they would be swallowed. And here you can see the sun here, if I can get this to work. The sun there is being swallowed, or the sun god is being swallowed by Nut. And then the sun will pass through her belly. You can see it passing through, and it'd be reborn at dawn. And so you think, well, why does the sun disappear at dusk? When the sun sets, where does it go? Well, it's being swallowed by the sky goddess Nut. And then every morning it's being reborn. So there's not this idea of the sun going around the earth even. It's this sort of, the sun disappears somewhere and it reappears somewhere else. How does it get there? And so you have these ideas that nature is alive, and these are divine forces, that nature is truly divine, from the sky to the earth and so on. Then we have your Greek philosophers. They were different in not really understanding nature as divine in classical cosmologies. But Plato still saw material substances and something he called as the ideal forms. Something like the ideal triangle is an eternal idea. And he saw these substances out of which everything's made also as eternal. In this way, matter was seen as pre-existing, and there was a divine architect who formed this formless matter in the beginning. But so you have matter is eternal, and the divine architect are eternal, and the divine architect forms matter. Aristotle and his Aristotelian successors also saw the universe as eternal, as having no beginning and no end, but he saw it as finite in space. Democritus and Epicurus, though, other philosophers, ancient Greek philosophers, argued for a universe of infinite space and infinite time. Pretty much a universe that actually existed forever, and that what creation occurs through a sort of combination of atoms in the void randomly. So here we have a very early and interesting and materialist idea of how we all got here in infinite space and time. The Genesis Cosmology, however, is quite different from these. Near Eastern scholar Ernest Lucas says that the Genesis account differs markedly from all other ancient cosmologies. The existence of the Creator is assumed, and there's no attempt to explain the existence of God, whether through birth or something else. God just is. And creation is accomplished solely by God's word. God speaks it, and it happens. And Ernest Lucas says, this indicates that the divine creative activity is voluntary, rational, and effortless. This way of speaking about creation. In all other ancient cosmologies, the physical universe is fashioned out of pre-existing material. However, in Genesis 1:1 we read, "In the beginning, God created the heavens and the earth." And this phrase, heavens and the earth, scholars often say is something called a merismus, which is this idea of it's like saying from head to toe. It's that your whole body hurts from head to toe. This idea, the heavens and the earth, scholars will say, means everything. God created everything in existence. And so there's a lot of scholars would say that this is actually referring to creation out of nothing, or what's called creatio ex nihilo, and that's from the Latin to mean creation out of nothing. Hebrew scholar Gerhard von Rad says the Hebrew verb bara, or create, contains the idea both of complete effortlessness and creatio ex nihilo, since it is never connected with any statement of the material. This word is never used in reference to God creating out of something, but rather that God is just creating. So what's the bottom line of Genesis 1 through 27? I'm not going to go into the details of this passage. Many of us know it well, but I would say that the bottom line, and we can talk about details later, is first of all, there was a time when everything was formless, void, and dark. There was a time before there was light. There was a time before the stars, sun, earth, and moon existed. There was a time before plants existed. There was a time before animals existed. And there was a time before humans existed. So all of these things had a beginning in time. And there was a time when all these things were not. While the creation of each of these things is treated separately in the Genesis account, and some of them are created from preceding things as well, we read in Genesis. The bottom line, the Hebrew theological vision of this passage is that ultimately everything in existence comes from nothing. And let that sink in for a second, the idea that everything in existence, everything you see around you, these chairs, the screen, all of us come from nothing. The whole universe comes from nothing. And this is a pretty profound concept when you let it sink in and reflect on it a bit. This was something we find very explicitly stated in the writings of early Jews, and this is from 120 years before Christ. The writer of a book called Second Maccabees says, "Look at the heavens and the earth and see everything that is in them, and recognize that God did not make them out of things that existed." So here's this idea that God did not make everything you see from anything that existed. It's pretty explicit there. We read this also in the New Testament. For instance, Paul says that God restores the dead to life and calls into existence those things that had not existed. Again, in Hebrews we read, "By faith we understand that the world was created by the word of God, so that what is seen was created out of things which were not." Again, this idea called creation ex nihilo. The doctrine of a creation out of nothing was the universal consensus also of the early church fathers who were living in the time when the New Testament was being formed. The writer of a very influential early book called The Shepherd of Hermas, Justin Martyr, Irenaeus, Tertullian, Theophilus of Antioch, Origen, Hippolytus, Basil of Caesarea, Gregory of Nyssa, Augustine, and so on, they all dramatically affirm this understanding that God created everything that exists out of nothing. Augustine, in fact, said that matter, space, and time are all created out of nothing, that time is part of the creation. Thus, Augustine says that time is part of the creation, and thus God created the cosmos with time rather than in time. And so here we have something that Einstein would actually prove many years later, but this idea that time is part of the creation, that time itself does not even pre-exist the creation. We even confess this idea in the Nicene Creed. As Christians, when we have communion in this church, we confess this. We believe in one God, the Father Almighty, maker of heaven and earth, and of all that is, seen and unseen. So God created everything. Theologian Karl Barth says the affirmation of creatio ex nihilo was theologically so significant that it became one of the firmest parts of the general teaching of the church concerning creation. So this idea of creation out of nothing is a fundamentally Christian idea that was unique to the early Jews and to early Christians in the ancient context, and something that Christians have always held so strongly, even when Christians were very strange in holding this. One example of this is John Philoponus. He was a firm believer in this idea of creation out of nothing, and he was also an early Christian mathematician and physicist who was living in the 500s primarily, a very early thinker. His work was foundational to the work of Galileo and other early modern scientists. And he defended the Christian belief in the finitude of the universe against the near complete consensus of the ancient world, of other philosophers who weren't Christians. He defended this idea. He rejected the Aristotelian eternal universe, eternal in time, and the Epicurean infinite universe in both time and space, based on this Christian idea of creation out of nothing. He also used sophisticated physical arguments against the Epicurean belief in the infinity of time, space, and the idea that there are an infinite number of stars. And one of his arguments went like this. He said, if the universe were infinite in the sense that the number of stars it contains is infinite, the light emitted by them would also be infinite, and therefore there would be no dark spaces in the universe. But there are dark spaces, and therefore the universe is finite. And so here's this idea expressed that if you were to look at an infinite number of stars that existed in an infinite universe, every direction you would look, there would be a star, right? And so the sky would actually be very bright rather than dark. So the very notion that we have a dark sky means that the universe had a beginning. Interestingly, this was restated about 1,000 years or so later by a guy named, an astronomer named Heinrich Olbers. And he investigated this puzzle of the dark night and said, well, the stars are evenly distributed throughout infinite space, and their absolute brightness is the same everywhere and at all times. The stars are at rest, except for local random motions, and the universe does not change with time. Therefore, something very strange that doesn't make sense, with these assumptions, then we shouldn't have the idea that the sky is dark, but rather the sky everywhere should be as bright as if it were the surface of the sun. And that was how Olbers formed this paradox. And this was a paradox that was really, really interesting. It's named after this guy, but he wasn't the first person to think of it. We'll revisit this in a second. But to go back to John Philoponus, he likewise found a contradiction at the heart of pagan Greek philosophy that had gone unnoticed for over 850 years, from the time of Aristotle to his own time. No one noticed a blatant contradiction at the heart of Aristotle and Plato's and everyone else's philosophy that held this view here. Aristotle and most other pagan philosophers argued there cannot be more than a finite number of anything. There is no such thing as a true infinity. Yet, Philoponus pointed out that the universe would have to pass through an infinite number of years if it had no beginning, as Aristotle argued. So if the universe was eternal, as Aristotle and other philosophers said, then it had to pass through an infinite number of years. But if there can be no true infinity, then the universe can't be eternal. You can't have both one and the other. You can't have an infinitely long universe and say there's no such thing as an infinity. And so here is a very obvious contradiction right at the heart of Aristotle's philosophy, and this was something pointed out first. John Philoponus was the first person who noticed that there was this contradiction. Aristotle and Ptolemy, after him, Ptolemy was the guy who was very influential in the European Middle Ages. They argued that the universe is eternal, again, no beginning and no end, but finite in space. But the universe was still big. They said the distance from Earth to the spherical shell of stars is 20,000 Earth radii, which calculates to about 80 million miles in diameter. And so they had this idea, if you see these stars around the shell, that the stars were fixed to a spherical shell that was the edge of the universe, and heaven was literally on the other side of that. Nicholas Copernicus accepted this basic idea of fixed stars on the edge of the universe in the shell sort of arrangement, but he says it was actually 200 times larger in diameter, and that was for a technical astronomical reason related to something called stellar parallax. He argued it was actually bigger than what Ptolemy and Aristotle said. It was an English astronomer by the name of Thomas Digges in 1576 who first introduced the idea that the stars are not attached to a spherical shell, but are spread out through space. And so Digges took the first dramatic step towards an infinite universe. He recognized that in 1517, he also recognized the puzzle of the dark night, but he didn't really address it at all in this idea. He was aware of this dark night puzzle from before, but he didn't address it. He just basically ignored it. But he thought that the stars, and you can see his drawing here, that these stars were actually heaven. So he didn't get rid of the idea of heaven, but what he did was he said the stars are heaven. So when we look at the stars, we're looking directly into heaven, and heaven's infinite, and therefore the space of the stars is infinite. So he didn't have a theological issue with doing this. Johannes Kepler, who came after Digges, however, he also he took the dark night puzzle seriously. This idea that the sky should be very bright if you have an infinite number of stars over an infinite space. And he argued that the darkness of the night sky directly conflicted with the idea of an infinite universe filled with bright stars. This led Kepler to believe that the universe was finite in extent. And so here we have, again, the same argument for the finitude of the universe coming from the brightness of stars. Kepler and Galileo, as well, in their science, were unable to explain why the planets move around the sun in elliptical orbits and what keeps the solar system together. And the reason why this is as important is because this problem in their thought led to a solution, which again led to an idea of an infinite universe. And that was by this man here, Isaac Newton. Newton's law of gravity provided the answer and explained Kepler's laws of planetary motion. It explained why does the solar system stay together and not fall apart. Newton argued that if the universe were finite, or if stars were grouped in one part of the universe, though, the gravitational forces would soon cause all stars to collapse into a huge clump at the center. But an infinite universe has no center, so it can't collapse. And so Newton solved this problem of Kepler's and Galileo's, but one way he was able to solve a bigger problem was through an infinite universe. And so gravity keeps the solar system from collapsing, but what keeps the universe from collapsing if it's finite? Well, if we don't have a center to the universe, which Newton said we'd have to have it if it was finite, therefore the universe must be infinite. And so he actually gets to this through physical principles. However, Newton also argued that the universe was eternal, and he did this for a number of reasons following a number of arguments that I won't get into today. Newton completely ignored the dark night puzzle. He knew it existed. He knew this paradox existed, but he completely ignored it. Then we have a man named Pierre-Simon Laplace, who brought Newtonian astronomy to its mechanical perfection. And with Laplace and other atheists, and Laplace was writing in the time of the French Enlightenment, an eternal mechanistic universe seemed necessary to avoid a divine creation for the universe. And so this idea of an eternal and an infinite universe sort of became fixed in the mid to late 1700s. And then we get to Einstein a couple hundred years later. Albert Einstein believed with most physicists since the time of Newton that the universe is static, eternal, and infinite. In 1914, though, when he was working on his theory of general relativity, which is a theory that deals with, it describes gravity as a geometric property of space and time. We won't get into the details of that right this second. But Einstein found that his equations portrayed a universe that was anything but static. And this was a problem for Einstein. So he purposefully modified his equations to come up with a different calculation. Einstein inserted what he termed a cosmological constant, represented by the Greek letter lambda, which he chose precisely to balance the attractive force of normal gravity, and lambda, this constant, functioned, in Einstein's words, to prop up the universe. The universe would collapse without this lambda, or it'd be expanding or collapsing, but it wouldn't be static. His equations indicated the universe was actually moving, so he put a nice constant that he chose precisely to balance the movement of the universe that would otherwise be implied by his equations. For Einstein, the main role of lambda, says historians of science Helga Krach and Dominique Lambert, was to keep the universe he grew up with. He didn't want to leave the universe he grew up with behind. He liked the static universe. So in this way, particular faith assumptions, metaphysical or philosophical assumptions regarding the nature of the physical universe blinded Einstein from actually deriving the correct physical interpretation of his own equations. And we can say this in hindsight because we know the history. Einstein's received cultural beliefs about the nature of the universe did not allow for him to envision an expanding universe with a beginning. Within his own metaphysical or faith framework, Einstein rejected solutions to his own equations that implied an expanding universe. As a result, he actually lost the opportunity to receive an additional Nobel Prize. He referred to this inability to see beyond the received understanding of the universe as one of the biggest regrets of his life, and this is much later, after a series of events we'll talk about. The first interesting one was Alexander Friedmann, who was also looking at Einstein's equations and in 1922 presented a solution of Einstein's equations which indicated the expansion of the universe. Friedmann was an Eastern Orthodox Christian, quite a devout Christian, who, against the prevailing view of the times, was willing to assume an expanding of space and time, and thus a beginning of space and time in working out of Einstein's equations. Cosmologist and historian Jean-Pierre Luminet says, for Friedmann, general relativity suggested the creation of the world by God. So he was open to this idea. He didn't find this a disturbing idea that there could be a beginning of the universe. Friedmann's Christian faith actually favorably disposed him towards a scientific interpretation, which Einstein would not and perhaps could not consider. Friedmann thought the Christian assumption about the nature of the cosmos as one having a beginning, as opposed to being infinite and eternal, was both theologically more sound and mathematically more consistent. So here we have his faith and his science working together to come up with what we now know as a correct interpretation. Another person who was very important in this story is this man here, Georges Lemaitre. He was an astrophysicist and a Belgian and Roman Catholic priest, as you can see from the picture here. Lemaitre was investigating Einstein's calculations during the 1920s and realized that something was not right about the insertion of Einstein's cosmological constant lambda. He noticed that Einstein's static lambda model of the universe was in fact highly unstable. It was balanced, but it was balanced on a knife's edge. With the slightest adjustment, the universe would either completely collapse or it would wildly expand. And Lemaitre thought this was sort of a strange thing here. He thus concluded that the universe was not static, and in 1927 proposed that it was expanding. Lemaitre noticed in his mathematical model of the expanding universe that the velocities of galaxies would vary in proportion to their distances from the Earth. Projecting that expansion back in time, he further concluded that an initial creation-like event must have occurred. This idea that the galaxies are expanded and there's this proportionality meant that if you turn back the arrow, then everything sort of goes to this point, which here is called a singularity. The idea that everything goes back to this point and you have some sort of odd creation-like event. But rather than rejecting this idea, which Einstein completely thought was disgusting, Lemaitre welcomed the idea of a cosmic beginning rather than finding it physically abhorrent, as many other physicists at the time did because of their belief in a static universe. And again, Lemaitre's Christian faith plays a huge role in his willing to think beyond what other scientists were willing to consider at the time. At a conference, shortly after Lemaitre published a paper on the expanding universe, he drew Einstein's attentions to his results. Einstein responded, "Your calculations are correct, but your physical insight is abominable. And so again, we have this idea that Lemaitre shows Einstein his calculations. The expanding universe idea, though, is completely repugnant to Einstein. Not only to Einstein, but even Lemaitre's mentor at Cambridge, Arthur Eddington, who was a famous British cosmologist. In 1931, he considered Lemaitre's idea of an expanding universe and says, philosophically, the notion of a beginning of the present order is repugnant to me. And he published this in Nature, in the journal Nature. He says, because this is a mere confusion between physics and theology of creation. This idea of an expanding universe is smuggling theology into science. Historian of science Helga Krach says, it is most remarkable that neither Friedman's nor Lemaitre's works made any impact at all. The reasons for the neglect are not entirely clear, but ingrained belief in the static nature of the universe was undoubtedly an important socio-psychological factor. These papers were published in all the right journals. They introduced the ideas to all the right people, but they resisted them to a person, pretty much. Lemaitre responded to Eddington, also in the journal Nature, and suggested, though, that the expansion of the universe, if projected back in time, meant that further in the past, the smaller the universe was, until at some finite time in the past, all the mass of the universe was concentrated into a single incredibly dense point, which Lemaitre called the primeval atom. And this is the earliest understanding of the Big Bang Theory. I'm not going to call it that because it's anachronistic at this point. But he says, at this primeval atom, the fabric of time and space came into existence. And so this is his first discussion of the Big Bang Theory here. And he says, though, the beginning of the world is a little before the beginning of space and time. And this is a very interesting phrase, a little before. And so you see all of space and time come into existence, but he says, but the creation is a little bit before that. So we're actually not looking at the creation. We're looking at the beginning of space and time, not the actual creation by the hand of God. And he says, therefore, this is not at all repugnant, using the word that Eddington said, because we can describe the origin of the present universe in completely physical terms. He said, this is not theology, this is actual science. Lemaitre's 1931 paper in Nature originally had references to God in it, but he removed them fearing it would bias other physicists against his interpretation. But it's interesting to hear the words that he took out of the manuscript in the proof version. He wrote, I think that everyone who believes in a supreme being, supporting every being and every acting, believes also that God is essentially hidden and may be glad to see how present physics provides a veil hiding the creation. So this idea that present physics gets you close to the creation, but there's still this veil. And he said, this should be encouraging for Christians that are out there. And he thought, I don't want to publish that in my Nature paper, because then everyone will certainly think I'm pushing the theological envelope. Historian of science John North says Lemaitre's science had a strong theological relevance for him. An initial singularity was not something to be avoided, but a positive merit, a token of God's creation of the world. And so again, we have this idea that Lemaitre was not going to look the other way when something looked like a creation event, because this was something positive for him as a Christian. At this time, though, it had long been believed that all stars were stationary. Again, you have this idea of a static universe that's not expanding. Edwin Hubble's analysis, and this is the astronomer Edwin Hubble, who was in Southern California, he first proved that that we weren't the only galaxy in the world, but there are other galaxies. And then his analysis of light from stars showed that the spectra of these galaxies were not even, but they were shifted towards one end of the spectrum of light. And this shift indicated that the distant galaxies were moving. And this is based on something called the Doppler effect. You can hear this with sound too. If a car is coming near you, it makes a different sound. If someone's laying on the horn driving towards you, you hear the horn getting closer, and it sort of has this sound, right? You also have that with light. Things moving away from you, the wavelength is lengthened. And so that's towards the red end of the spectrum, and the infrared. If they're moving towards you, it's towards the blue end of the spectrum. The wavelength is shortened. So you can actually tell movement by where things are in the spectrum of light. Most scientists expected the movement that Hubble detected to be random. They thought, well, if the stars are moving, they must be in a random organization, right? Hubble's results were nothing less than a bombshell to the community of physicists. First, he found that every galaxy's light was redshifted, meaning that every galaxy was moving away from us. Second, the speed at which a galaxy was moving away from us was directly proportional to its distance from us. Now, you've heard something very similar to that sentence a few slides ago. This was the exact same law of proportionality, which today is called Hubble's law, regarding the velocities of galaxies to their distances that was predicted by Lemaitre in 1927 and then discovered by Hubble to be the case for the real universe in 1929. And so there's recently been an attempt to rename that the Lemaitre-Hubble law or something like that, but it hasn't been successful because people generally still don't like Lemaitre, I think for interesting reasons we'll get into regarding his role as a Christian. But interestingly, this idea, Hubble discovered the same exact thing that Lemaitre predicted in his model 2 years earlier. The result of this was that Einstein, seeing the visual proof of an expanding universe from Edwin Hubble's findings through his telescope, relented and agreed with Lemaitre that his calculations were indeed the right ones, and by extension, his physics, quote, first rate. So his physics were no longer abominable, they were first rate. This still did not lead to a general acceptance of Lemaitre's theory of the primeval atom. People still did not buy his theory. In fact, during the 1930s, other cosmologies were proposed to explain Hubble's observations. And one of them was proposed by Einstein himself, and this was a cosmology of an oscillating universe. That, okay, the universe might begin in a singularity, which is pictured here, but perhaps it expands and then retracts and expands and retracts, and so you have this endless expansion and retraction of the universe through all time. So again, it's like, okay, Lemaitre might be right about the expansion, but he's wrong about the beginning. So there's this idea here that Lemaitre's theory still isn't generally accepted. In fact, it was actively opposed by fellow cosmologists on explicitly theological or metaphysical grounds. And the picture of this person here is Fred Hoyle, who was the greatest opponent to Lemaitre's Big Bang theory, and here we get the term Big Bang. Hoyle, in fact, gave Lemaitre's theory that name, the Big Bang, as a way to poke fun at it. And he gave it during a 1949 BBC radio broadcast, and the name stuck. We all think of the Big Bang, not the primeval atom. There's even a show called the Big Bang Theory, right? And so here we have this sort of like, the idea that we all came from this Big Bang is ridiculous. And Hoyle, extremely annoyed by the theistic implications of Lemaitre's theory, developed a rival physical theory called the steady state theory, and even popularized it on a series on BBC radio. Now, Hoyle was an extremely prolific and popular writer. His steady state theory got extremely popular. I read that his royalties from one of his books on the cosmos was 6 times his salary at Cambridge as a Cambridge professor. And so that's just from one of his books. So he was very popular. But Hoyle's atheism was a key motivator in the development of this alternative theory, as it was in his lifelong refusal to accept the Big Bang theory. Historian of science Edward Davis tells us precisely because he did not believe in God and because he did not like the implications of Lemaitre's theory, Hoyle ridiculed it and proposed the steady state theory to provide an alternative explanation without the implication that the universe had a beginning. And so here you definitely have faith assumptions motivating science all throughout this story. But that isn't the end of the story. In the 1940s, the Big Bang theory was further developed by people like George Gamow and Robert Herman and others. And they predicted in 1948 that if the Big Bang was an accurate picture of the universe, then there should be an afterglow of something called microwave radiation present throughout the whole cosmos. And the abbreviation for that is CMBR, cosmic microwave background radiation. And this radiation, they said, would have cooled by now, billions of years later, to about 5 degrees Kelvin, or negative 268 degrees Celsius. They also predicted the levels of hydrogen and helium in the universe, what those levels would be as a consequence of reactions that occurred during the Big Bang. And so they had some pretty clear predictions of what you would see if the Big Bang really happened. But during the 1950s and through 1964, again, a historian of science, Helga Kroc, tells us the Big Bang theory was dead. He says, completely dead. There was one paper in 15 years published on it. It was still associated dramatically with Lemaitre's Christian perspective. In fact, one Russian cosmologist in 1956 called the Big Bang an unscientific popish conclusion. So there's this idea, this is popish science, right? Roman Catholic science, and it's unscientific, this idea of a creation. Interestingly, though, Hoyle's view, which was very popular at this time, was not rejected, even though it was clearly motivated publicly by Hoyle's atheism. So the idea that you could clearly reject Christian-motivated science, but not atheistic-motivated science, is something interesting to think about. But then in 1964, two radio astronomers named Arno Penzias and Robert Wilson accidentally discovered and confirmed the existence of the cosmic microwave background radiation at 3 degrees Kelvin, just 2 degrees lower than the 1948 prediction. Let me say a word about that first. This idea of the cosmic microwave background radiation that was discovered by Penzias and Wilson happened through a series of them trying to eliminate all this exterior noise from their antenna, because they were trying to listen to very faint sounds from these weather balloons that they were trying to listen to. And they couldn't get rid of this radiation. So essentially, this idea that this radiation was everywhere was confirmed by them. Then in 1992, the NASA satellite, the Cosmic Background Explorer, or COBE satellite data, showed a perfect fit between what the Big Bang theory predicted about something called the black body radiation curve, which you see in this image here, and what was observed in the cosmic microwave background radiation. So again, the point of this is that the COBE satellite took what we can think of as baby pictures of the universe, only about 300, 400,000 years after the universe came into existence, and that the picture of this universe coincided precisely with what Big Bang theory predicted. As a result, the Big Bang model is now accepted by the vast majority of cosmologists, and it's known as the standard cosmology. There's also been some amazing recent evidence which has substantiated the Big Bang picture of the universe and has helped us to better understand our own historical place in the cosmos. And this evidence has to do with the finite travel speed of light, that looking out into space is also looking back into time. The most distant objects visible in our telescopes actually carry us back in time to within a couple billion years after the Big Bang, when the universe was much smaller and all the galaxies were much younger. One of the most dramatic pictures, some of the most dramatic pictures taken with this idea that going further out takes us back in time, is from the Hubble Space Telescope and their 250-hour deep field exposure, which is described as something like core drilling through space and time. So what we have here is what we see as, and we see this in this image here, that as the exposure continues, you get deeper and deeper into space, so you can actually see the evolution of the universe through these images. And what we see when we watch this evolution of the universe is large mature galaxies are present in the foreground, giving way to roughly 10 billion years ago to small, unformed, lumpy proto-galaxies that are in the process of formation. Then finally, space becomes empty as we fly past the earliest galaxies and into the cosmic dark ages, the pre-galactic era before any galaxies had formed. So you keep looking back, and then there are no galaxies, which is exactly what Big Bang predicted, that the cosmos has a history, that there was a time before the galaxies existed. And so we see this very clearly from the Hubble telescope. And here's another image which conveys this idea of looking back into space. You look in the foreground, you have mature formed galaxies, and then you have proto-galaxies back here. And this is a more recent, there's also the Hubble deep field and the Hubble ultra deep field. The ultra deep field goes back to about 700 million years, 400 million years after the Big Bang, whereas the first one went to about 1 billion years after the Big Bang. And so this is some pretty amazing stuff. So from all of this, I would like to briefly give you a brief history of the cosmos from the point of the Big Bang forward. The universe began in an unimaginably hot, dense state about 13.8 billion years ago. This is the point at which both space and time begin, and it's often referred to as t equals 0 or time equals 0. This initial state is called a singularity, and it's described as a point of infinite density and 0 volume. And so that's a pretty strange phrase if you think about it for a second. Infinite density, 0 volume. Then what we have is immediate after this, from 0 seconds to 10 to the negative 43 seconds. And if you're not familiar with exponents, that means point, right? And then 43 zeros and then a 1 second. So it's a very tiny fraction of a second we're talking about. I was going to write it out, but it took up too much of the slide. So very tiny fraction of the second. And what we have here is what's called the Planck epoch. And this is, Planck time is the shortest possible interval of time. This is a period of extremely high temperatures. It's a period that we actually know very little about. It's where the standard Big Bang model breaks down. During this period, it's believed that because the universe was so small, quantum physics actually kicks in. And so you have to understand the universe according to quantum principles at this time. But again, little known is about this period of the universe, and it's somewhat mysterious. This is the realm of something called quantum cosmology. And there's no standard quantum cosmology. It's sort of anyone's game at this point. A new physics, a genuinely new physics is needed to understand this stuff, which requires a quantum treatment of gravity and such. But this is the Planck epoch. We'll talk about this more next week. It's very small, but very important for this understanding of a beginning or not, and the question of where does everything come from. Immediately after this, we have what's called the inflation phase. Again, very tiny fraction of a second, from 10 to the negative 35 to 10 to the negative 32. During this time, very brief instant, our entire visible universe, which is now 30 billion light years across, is inflated by a factor of 10 to the 60, from an indescribably small speck to about the size of a grapefruit. Immediately after this period of inflation, the cosmos begins to expand normally. After 10 to the negative 32 seconds, the universe is 10 to the 27th degrees Celsius hot, a seething hot soup of energy and fundamental particles, things like electrons, quarks, neutrinos, and many other strange particles. Our 4 fundamental forces, which we'll talk about in a second, are still unified. And then at 1/millionth of a second, the universe has cooled down to a cozy 10 to the 13th degrees Celsius. The 4 basic forces, physical forces, become distinct at this point. First, we have gravity separates, the force of gravity. Then what's called the strong nuclear force, which holds the nuclei of atoms together. Then the weak nuclear force, and then the electromagnetic forces all separate. Fundamental particles join together to form protons and neutrons. At 3 minutes after the Big Bang, the universe is still quite hot, but protons and neutrons come together to form the nuclei of simple elements, 75% hydrogen, 25% helium, and trace elements of lithium. It's still too hot for electrons to be captured into orbits to form stable atoms. And thus, we have also this interesting thing that charged electrons and charged protons prevent light from shining. So the universe is completely dark at this point. There's no possibility of light shining. Another interesting detail is that if you think about space now as a vacuum, at this point, the density of the universe was that of around water. So the density of water, if you think of swimming, that's sort of the density of the universe at this point. 300,000 years after the Big Bang, still quite hot, but stable atoms of hydrogen and helium form. The universe then becomes transparent. Light shines out in the darkness for the first time. So this is the first time we can see light in the universe. And this is also the time to which the microwave background radiation goes back to. This is where the background radiation originates from, and thus gives us a direct picture of how matter was distributed at this early time. And again, this is sort of the baby pictures of the universe 300,000 years after the beginning. About 1 billion years after the Big Bang, the universe has cooled down quite a bit. Gravity amplifies slight irregularities in the density of the primordial hydrogen and helium gas. And these pockets of gas become more and more dense, and stars ignite within these pockets. Groups of stars become the earliest proto-galaxies. And this is the period to which the Hubble Deep Field can see. Now, stars are extremely important for the universe. Without them, the universe would have remained chemically impoverished, and therefore, you'd never have biological life without this first generation of stars. Up until the formation of stars, the only elements present were hydrogen, helium, and a little bit of lithium, which is the lightest metal. All the other elements, including carbon, oxygen, iron, and everything else, are being built up in the cores of this first generation of stars, where the temperatures reach hundreds of millions of degrees. After 9 billion years or so, the most massive stars explode as supernovae. Subsequent generations of stars are then formed out of material enriched with the heavier elements that are formed during the first generation of stars. Hence, newer stars, like our own sun, also have planets. All of these events that we discussed set the stage for the birth of our own home, the solar system, about 9 billion years after the Big Bang, or 4.6 billion years from the present. Or before the present, not from the present. The chemical elements of which Earth and everything in it, right, everything that we see on this Earth pretty much, including us, are made, everything that's, everything of which we are made and everything's made, were built up inside the cores of earlier generations of stars. And we can see sort of the chemical composition of one of these early stars here, with iron at the middle and silicon, oxygen, carbon, all the things that go into our bodies were all formed in these early generations of stars. So that's the Big Bang. What is the nature of the Big Bang? What was it like? If you go on the Answers in Genesis website, which is a young Earth creationist website, they'll show explosion after explosion, the Big Bang, and they'll show, there's a video of a car exploding inside of a garage. And it says, well, that just creates chaos. It doesn't create something interesting. So was the nature of the Big Bang a huge explosion? Or was it something more like a symphony orchestra? Something very finely tuned, very organized, very structured. George Smoot, who was the cosmologist and winner of the Nobel Prize for his work on the COBE satellite, who was actually here at Berkeley when he did that, says the Big Bang, the most cataclysmic event we can imagine, on closer inspection appears finely orchestrated. Stephen Hawking says, if the rate of expansion 1 second after the Big Bang had been smaller by even 1 part in 100,000 million, the universe would have recollapsed before it ever reached its present state. So this was an extremely fine-tuned, very precisely orchestrated event. For instance, if we will look at one part of this that's very important for the early expansion of the universe and and how elements come together and such, something called the initial distribution of mass energy, we might ask, how precise was this? Roger Penrose, who's a theoretical physicist and cosmologist, says, in order to produce a universe resembling the one in which we live, the creator, and he's talking about a hypothetical creator here, would have to aim for an absurdly tiny volume of the phase space of possible universes, about 1 over 10 to the 10 to the 1/23rd, that's a double exponent, of the entire volume of phase space for the situation under consideration. And then he says, the pin and the spot aimed for are not drawn to scale, which I think is very funny. But so how big is this number, he's saying? Well, he said, if you were going to try to write this down, you couldn't physically, ever. If you were to write on every quark, every lepton, every fundamental particle, if you were to write a 1 and then try to write all the zeros, you wouldn't have enough fundamental particles in the entire universe to write down this number. You could throw in he says, throw in neutrinos if you want. You cannot write it down. That's how big this number is. So extremely finely orchestrated, precisely orchestrated event to get the universe we live in. So it wasn't a cataclysmic, random, chaotic explosion. According to Penrose's calculations, the precision of the Big Bang explosion must be much greater than that needed to blow up a pile of rubble and obtain a fully formed building replete with tables, chairs, and computers. And so you need to blow up a pile of rubble and end up with an office building and everything in it. That's a smaller level of precision than is required for the Big Bang to come up with what it came up with. So the Big Bang was clearly an incredibly fine-tuned and precise, well-orchestrated event, to say the least. Does that, however, mean that we are living in a created cosmos? Is the Big Bang a creation of the universe from nothing? Well, Cambridge cosmologist, theoretical physicist, and mathematician, actually former attendant at Berkeley Covenant Church, John Barrow says, at the singularity, space and time came into existence. Literally, nothing existed before the singularity. So, if the universe originated at such a singularity, we would truly have a creation out of nothing. However, others would point out that our ability to really truly say what happens before the Planck epoch, where space and time break down, means we do not and may never really know whether the universe truly came from absolutely nothing or from some earlier state which will be forever veiled from our scientific eyes. Perhaps you had a perfect balance of antimatter and matter, right? Which would give you literally nothing, but that's still something. There's still physics involved there. Other cosmologists, Starobinsky and Zeldovich, say we cannot prove the creation of the universe from nothing, but the creation of the universe from nothing is not prohibited by any basic physical law. So it's sort of like, well, we really can't say one way or the other. Other two well-known cosmologists, Stephen Hawking and George Ellis, in their classic book, The Large-Scale Structure of Space-Time, say the results we have obtained support the idea that the universe began a finite time ago. However, the actual point of creation, the singularity, is outside the scope of the presently known laws of physics. At the very beginning of this universe, then, we are confronted with a profound and mysterious question mark. A question mark that the physics as we know it, is in principle not able to remove. So we're stuck with this question mark. How does this make us feel? Well, Robert Jastrow, a NASA astronomist, physicist, and cosmologist, who's not a Christian, he's an agnostic, says, for the scientist who has lived by faith in the power of reason, the story ends like a bad dream. He has scaled the mountains of ignorance. He is about to conquer the highest peak. As he pulls himself over the final rock, he is greeted by a band of theologians who have been sitting there for centuries. And so that's where we are today. If you want details of this lecture or want to read more, I recommend highly Theology and Modern Physics by Cambridge, the late Cambridge, or no, not Cambridge, Oxford, excuse me, Peter Hodgson. A very readable book. This book's also very readable, God, Creation, and Contemporary Physics by Mark Worthing. If you want something that's more technical, less readable, but still very interesting, and under $60, Michael Heller's book is a very up-to-date, and he's actually a Roman Catholic cosmologist, so you get a very interesting perspective because he's a very distinguished cosmologist, but also a believer in God. So he gives a very interesting perspective on the more technical side.